In this video we introduce the idea of a geometric sequence. On his first birthday, Auntie Hayley plans to give her young nephew, Harrison, £50 and plans to increase the present each year by 5% until he reaches his 18th birthday. We want to discover how much will Harrison receive from Auntie Hayley on his 15th birthday and how much will he have received altogether by the time he has celebrated his 18th birthday. On his first birthday then, Harrison will receive £50. On his second birthday he's going to receive 50 times by 1.05, which is £52.50. On his third birthday he will receive 50 times by 1.05 times by 1.05, in other words 50 times 1.05 squared, which to the nearest penny gives us £55.13. On his 15th birthday, the initial amount of £50 will have been multiplied by 1.05 14 times. So you will receive 50 times by 1.05 to the power 14, which gives us £99 to the nearest penny. In general, Hayley will give Harrison a present of QN pounds for his nth birthday, where QN is 50 times by 1.05 to the n minus 1, provided n is an integer between 1 and 18. This sequence that we've got here, 50, 52.5, 55.13, etc., is an example of a geometric sequence. We can use the sigma notation on our calculator to calculate the total amount that Harrison will receive after he's celebrated his 18th birthday by working out the sum between 1 and 18 of Qn, the amount he receives on his 9th birthday. So that's the sum between 1 and 18 of 50 times 1.05 to the power n minus 1. And using our calculator we should be able to show that that is £1,406.62. In the next video we'll find a formula giving the sum of the terms in a geometric sequence. But in this video we're just going to continue looking at geometric sequences and how to deal with them algebraically. So a sequence such as the one we've just been looking at, in which each term is obtained by multiplying the previous term by a constant number, are called geometric sequences or geometric progressions. The number which each term is multiplied by to obtain the next term is called the common ratio of the sequence. And provided we know the first term and the common ratio of a geometric progression, then it's possible to write down as many terms of the sequence as we wish. So for our first example, we've got a geometric progression has first term 300 and common ratio 0.8. We're asked first of all to write down the first 5 terms of the sequence. The first term is 300, the second term is going to be 300 times by 0.8, which is 240. The third term is going to be 240 times by 0.8, which gives me 192. The fourth term, 192 times 0.8, which is 153.6. And the fifth term is going to be 153.6 times by 0.8, giving me 122.88. Now notice that the second term is 300 times 0.8. The third term is 240, or 300 times 0.8, times by 0.8 again, so it's 300 times 0.8 squared. The fourth term is the third term, times by 0.8, so that's 300 times 0.8 squared, times by 0.8, which means that the fourth term is 300 times 0.8 cubed. And the fifth term is the fourth term, times by 0.8, so that's 300 times by 0.8 cubed, times by 0.8, in other words 300 times 0.8 to the power 4. So the 20th term is going to be 300 multiplied by 0.819 times, in other words the 20th term is 300 times by 0.8 to the 19, which is 4.323. to 3 decimal places. And the nth term is going to be 300 multiplied by 0.8 n minus 1 times. In other words, the nth term is 300 times by 0.8 to the power n minus 1. A more general geometric sequence has a first term of a and a common ratio of r. So the first 5 terms are going to be a, ar, then ar times r, which is ar squared, then ar squared times r, which is ar cubed, and then ar cubed times by r, which is ar to the 4, and so on. The 80th term of the sequence will be a times by r 79 times, or ar to the power 79. And the nth term in the sequence will be ar to the power n minus 1. So we have our first important result about geometric sequences, which says that for a geometric sequence with first term a and common ratio r, the nth term is going to be a times by r to the power n minus 1. So in example 2, we're going to calculate how many terms there are in the geometric sequence 3, 6, 12, 24, etc. up to 393,216. We've got a geometric sequence in which the first term is 3 and the common ratio is 2. If there are n terms in the sequence, then 393,216 is the nth term in the sequence, which is 3 times 2 to the power n minus 1. Dividing by 3 gives me 131,072 is 2 to the power n minus 1. And the easiest way now of proceeding is by taking logs to base 2 of each side. If I take logs to base 2 of each side, I've got log to base 2 of 131,072 must equal n minus 1. And using my calculator, that gives me 17 equals n minus 1, so n equals 18. If your calculator hasn't got logs to any base on it, but has only got logs and natural logs on it, then we can still get through the question by just using a slightly alternative means. We use logs to base 10 and we just go through the process as shown in the blue box here. For example 3, we've got a geometric sequence has third term 144 and seventh term 729. We've got to show that there are 2 different possible sequences satisfying this condition, and we've got to find the first 4 terms of each of these sequences. If a is the first term and r is the common ratio, then we're told the third term is 144, so that tells me that ar squared must be 144, and we're told that the seventh term is 729, so I've got 729 equals the seventh term, which must be ar to the power 6. If I take equation 2 and divide it by equation 1, I get ar to the 6 divided by ar squared equals 729 over 144. Now clearly the left hand side simplifies to r to the 4, and the right hand side is equivalent to 81 over 16. So I want the fourth roots of 81 over 16. Well, if r to the 4 is 81 over 16, which means that r must be plus or minus 3 upon 2. The fact that I have got r squared is 9 over 4 means that equation 1 tells me that 144 is 9 over 4 times a, so a must equal 64. So the sequence must have a first term of 64, and then it's got a common ratio either of plus 1.5 or minus 1.5. If r is 1.5, then the first 4 terms are 64, 96, 144, 216. On the other hand, If the common ratio is minus 1.5, then the first four terms are 64 minus 96, 144 minus 216. That concludes our first look at geometric sequences.